Hi everybody, I'm Hengguan from US. I'm going to talk about FedNP towards non-IID federated learning via federated neural propagation. I present a new perspective on handling non-IID federated data by explicitly considering the global data distribution during local training. So non-IID federated learning refers to scenarios where the feature distribution of federated parties or clients are totally different. So taking image classification task as an example, training data for one client may be just dogs, while the other client may be just cats and so on. Such problem setting is very tough and could increase the difficulty of model training. Actually, the key challenge for non-IID federated learning is the local model drift. Such problem makes the local model drift away from the global model as training steps goes by. There are two types of related work for mitigating such problem. The first type is about using global models or local model from previous turns to regularize local models, such as FedProgs and Skyford and so on. The second type of approach focuses on improving the global model aggregation, what we call the ensemble-based method. Next, I'll briefly introduce two typical existing methods. So let's first take a look at the FedProgs, a type of regularization-based method. So compared to the vanilla Fed average, FedProgs has an additional regularization term, aiming to prevent local model from drifting away from the global model. But such regularization sometimes leads to biases, depending on particular design of the additional loss. So FedBE is a typical ensemble-based method. It adopts Bayesian ensemble to provide a better global model aggregation. Specifically, FedBE intends to infer an unbiased parameter distribution given the local updates. However, such method requires a global dataset containing all clients for model training, which is not always available in practice. Okay, so before diving into the details of FedNP, let's first consider a toy example. So suppose we have a polynomial curve, y equals to minus x squared plus 2 times x plus 5. So to construct an extremely non-IID dataset, we sample 3 segments of this curve, shown as the red, green, and blue dots on figure 1. So our goal is to estimate the coefficients of this quadratic function using federated learning. According to our experimental results shown in the figure B and C, we find that local drift is the way too large to the degree that they cannot be fixed by these two typical existing federated learning algorithms. Okay, so can we approximate the global distribution through partitioned local observations? Answer is yes. Actually, the solution presented in this work is inspired by expectation propagation, an approximate Bayesian inference method. And such method does not require access to global data and hides the potential to approximate the global data distribution. So due to the limited time, I'm not going to discuss the details of EP algorithm. It's highly recommended to read our paper. Okay, so we encounter two major challenges when applying EP to federated learning. First, the EP requires calculating the likelihood term. But here the theta k, which is the model parameters for the current mini batch, such term is unavailable during training as we only have model parameters for previous mini batch. Additionally, the moment matching step in EP is computationally expensive, as it requires numerical approximations or sampling. So to overcome these challenges, we formulate EP by factorizing the latent global data distribution into a special form, such that likelihood term is not required. Based on such factorization, we propose a closed form update for estimating the global data distribution efficiently. Okay, so actually there have also been efforts to combine the expectation propagation with neural networks. But these methods are either not guaranteed to converge or not scalable to large datasets or complex neural networks. Generally, our problem follows a typical non-IID federated learning settings. Specifically, suppose we have k clients. Each follows a distinct data distribution pk of capital X, assuming a sequence of the model parameters theta k and the data xk are conditionally independent given the latent variable z. We aim to approximate the latent global data distribution pz given capital X. Our final goal is to adopt such global distribution to regularize local models and prevent them from sinking into local data distributions. And our final objective for the local training is the following. It has two parts. The first part is the original local training loss. We further add an KL term to such loss, allowing local models to be regularized by the latent global data distribution. Okay, so here we briefly present the key ideas of our FedNP algorithm. The key of FedNP is a special factorization of PZ given X, the posterior of interest. So by Bayes' theorem and assuming a uniform prior, as well as a bit of massage, we find that the posterior of the global data can be factorized by the product of the posterior of the local data. So based on this, then we can roughly follow EP update steps, for example, to derive the form of cavity and hybrid distribution. However, the moment matching steps are not computationally intractable. We therefore propose a closed form approximation for the approximate posterior by theorem 1 and 2 in the paper. So if you are interested, please check our paper for the proof. Okay, so we first evaluate our method on the toy data sampled from the polynomial curve. Generally, our FedNP achieves the lowest MSE comparing to baseline federated learning algorithms such as FedAverage, Moon, and so on. We further visualize the trained local models and the global model in subfigure B and C. As you can see, the FedAverage can fit the data points locally and yet fail to generalize well globally. Our FedNP is more robust, which is shown in the subfigure C, and the estimated global model distribution is more accurate, shown in the subfigure D, which corrects the local training and avoids performance deterioration. So we further test the FedNP on CIFAR 100 and Tiny ImageNet. So the left table shows the top 1 test accuracy of all approaches with the time client default setting. We can see that FedNP consistently outperforms both the Non-IID SOTA baselines and Bayesian federated learning baselines. We reach a similar conclusion by increasing the number of clients to 50 and 100. These demonstrate the effectiveness of the proposed FedNP. We also conduct a qualitative study of the FedNP. We randomly sampled data from the first 10 classes of CIFAR 100 and utilized TSNE to visualize the features produced by the FedNP. We got 2 interesting findings. First, FedNP is capable of learning more discriminative features among classes. If you compare left and right figure per cluster, you can find that FedNP achieves more inter-class compactness and larger inter-class margins. Second, FedNP is able to preserve the structure of global data distribution even the class distribution are extremely imbalanced. In contrast, the data distribution learned by FedAverage is relatively messy. To evaluate the computational efficiency and the approximation accuracy of the proposed closed form updates, we compare our FedNP with code FedNP, which adopt numerical conjecture-based method for the moment matching steps. Even if the code FedNP is implemented by a very efficient numerical approximation toolkit optimized for the GPUs, our FedNP still runs 2.4 times faster while achieving close approximation accuracy. So we finally evaluate FedNP on a natural real-world non-IID speech datasets for automatic speech recognition. Again, our FedNP achieves around 4.6% absolute WR reduction compared to the Fed average baselines, which is a large margin in ASR. FedNP also outperforms other typical federated learning algorithms, demonstrating that our FedNP can be generalized to real-world non-IID federated settings. Finally, here are a few takeaway points. We propose FedNP, which is the first sampling-free and end-to-end probabilistic neural networks for non-IID federated learning. We find that it's essential to incorporate the global data distribution for local training. And we overcome the technical challenge of applying EP to federated learning by first reformulate the posteriors into a special form and then derive a closed form approximation of the global data distribution. We also obtain superior performances on both synthetic and real-world image and speech data compared to several state-of-the-art federated learning algorithms. Thank you.